All right, we're going to try and go through our 14.2 notes, talking about the limits going back to last week when we talked in 14.1. So you may want to take a look at those notes before taking a look at this video. But a couple definitions with respect to the limits. Right off the bat, we're going to talk about the limit of a constant and then the limit of x, when it's just a variable. Throughout this lesson, we'll also tackle the limit of a sum, limit of a difference, limit of a product, limit of a quotient, and then other algebraic properties, power, taking an nth root, things like that. We'll look at polynomials, and lastly, the average rate of change. So all those things are going to be covered in this video. I'll go pretty fast. Feel free to pause at any time and give these a try, either in the notes or for homework. And if I need to break it into two videos, I will to get it to work. But for the first one here, the limit of a constant, f of x equals b. If I take the limit of, it could be just y equals 4. So the limit as x approaches any number of 4. So the limit as x goes to, let's just pick a number, 7 of 4. Well, that's going to just be equal to 4. Because as you could see down here, that regardless of what your c value is for this horizontal function, the y equals a number, b in this case, it's going to be approaching that regardless, anywhere you're going. So the limit of a constant is equal to that constant. The limit of x is actually now going to be equal to a number c. So the limit as x approaches, let's say, 5 of x. So now I'm looking at this guy here. That's going to be equal to 5. And that's demonstrated in figure 6 here, where this one-to-one relationship exists. So as I get closer to c, as I approach c for x, the y value is going to be approaching c as well. So whatever that c value is the limit. We've got a couple more examples here. The first one, this is the limit as x approaches c of a constant. Let's just show the rule here of b equals b. And then, for example, over here, the limit as x approaches c of x is equal to c. So just demonstrating the rules, and then you've got another limit of x here and limit of a constant there. Now on to some of our rules. So like I said, sum, difference, product, quotient, power, all those rules we're going to be talking about here. So looking at the rule here, and I'll write this one out. The limit of a sum is equal to the sum of the limits. And that's going to be the general flow of this. They're going to work fairly intuitively. Now, I understand that you could plug the numbers in, but not until I tell you that you can not do that. I need you to show me the limit. So from beginning to end, the limit as x approaches -3 of x plus 4 is going to be equal to the limit as x approaches -3 of x plus the limit as x approaches -3 of 4. And according to our limit of x rule, this is going to be equal to -3. The constant rule, that's going to be equal to 4. So the limit as x approaches -3 of x plus 4 is equal to 1. The limit of a difference is equal to the difference of the limits. So it's going to work exactly like the previous problem. So we'll just jump straight to the limit as x approaches 4 of 6 minus the limit as x approaches 4 of x, which is equal to 6 minus 4, which is 2. Hopefully you're anticipating these answers as we're going. The limit of the product is the product of the limits. So if you want to give this one a try, pause, give it a shot, and then pick up. But the work associated with this product, because we're multiplying negative 4 times x, this is the limit as x approaches negative 5 of negative 4 times the limit as x approaches negative 5 of x. Constant rule says that this is equal to negative 4, x is negative 5, and it's a product, so we get 20 as our answer for the limit as x approaches negative 5 of negative 4x. So these are a couple examples kind of combining those rules that we just talked about. We have a product and a difference in the first one, and then we have some products in the second one. For A here, we'll just go through them really quickly. The limit as x approaches negative 2 of 3 times the limit as x approaches negative 2 of x minus the limit as x approaches negative 2 of 5. And since it's a difference, you don't have to put negative 5. It's the difference of the limit of 5. Constant rule says this is 3 times negative 2 for the linear x rule minus our constant rule, which is 5. Let's see, that's negative 6 minus 5, negative 11, all said and done there. And then for B, we have the limit as x approaches 2 of 5 times the limit as x approaches 2 of x. And we'll talk about the power rule in just a second, but we could just treat it as another multiplication as x goes to 2 of x. So our constant rule is 5. This is 2 and 2. So we end up with 20 as our answer to that guy. So hopefully those worked out for you. If we have x raised to a power, a positive integer power, then we can evaluate it with the limit value as x approaches c. Whatever that c value is going to be taken to that power. So because we have this in the form of our new rule for a monomial, this is equal to negative 4 times 2 cubed, which we can evaluate. What is that? Negative 4 and 8 is negative 32 is going to be that rule. What this rule does for us is it kind of takes away the limit of 4 times the limit of negative 4 times the limit of x times the limit of x times the limit of x. We can just use the monomial rule. And this is the one you've probably been waiting for, the limit of a polynomial. Now that this rule has been established, this is saying effectively, now we can plug in. And that's going to save us some work here. I wouldn't want you to write the limit of this product, this difference, this product, this sum, this product, and all these powers and all that kind of stuff. Because it's a polynomial, and we know that the polynomial behaves in a continuous way. This happens to be a positive 4th degree function, so maybe I'll just make it kind of look like that. That there's no gaps, there's no breaks. If I pick a value c here, that it's headed towards some number, and that number is the f of c, or in this case p of c. So in this problem, the limit as x approaches 2 is going to be the result of plugging 2 into the polynomial. So we'll go ahead and do that and knock out all of this. We've got 80 minus 48 plus 12 plus 8 minus 2. Let's see, we've got minus 50 and 100. It's 50. There we go. So that would be the limit as x approaches 2 of that polynomial. The power or square root rule, which is really the same thing. Remember that raising something to the n power and raising something to the 1 over n power becomes the root. So this is equivalent to 1 over n is equal to the nth root. Let's write it like that. There we go. So they're really effectively the same rule. If you have the limit of something, of a function to some power, you could take the limit of the function and then take the whole thing to that power of n. Same rule applies for the root. So we'll rip through these 3 examples pretty quickly here. Again, pause if you want to give them a shot before watching me struggle through it. So the limit as x approaches 1 of 3x minus 5, and the whole thing I can raise to the 4th power. And because it's polynomial, I can plug it in. I get negative 2 to the 4th power, which is 16. For the second one, the limit as x approaches 0 of 5x squared plus 8, I could take this entire thing and square root it. Square root the entire limit, which is the square root of, when I evaluate that with 0, I get 8. Square root of 8 is 2 rad 2. Now the last one, if you remember this rule here, that 1 over n is the nth root. Since this is 4 over 3, this is actually going to be the cube root of the limit as x approaches negative 1 of 5x cubed minus x plus 3, and then the whole thing to the 4th power, which is equivalent to taking the entire limit to the 4th power and then cube rooting that entire thing. So I'll write the equivalency here. The limit as x goes to negative 1 of 5x cubed minus x plus 3. If I take this whole thing to the 4th power and then cube root the whole thing, it's really the same. It doesn't matter whether you do the cubed rooting first or the raising to the power. I think it's a little bit cleaner the first way I have it written. In any case, you end up with the cube root here of negative 1 to the 4th power, which is 1. So either way there. We hadn't yet gotten to the limit of the quotient. The only hiccup here is we just have to make sure that that denominator doesn't go to 0. That's the only restriction here. And to be honest, in many of the quotient problems, it will go to 0. This first one we're fine, but the exercise will be, okay, well, when it does go to 0, what can I do? What strategy can I use? Now this one, looking at the limit as x goes to 1 of 5x cubed minus x plus 2 over the limit as x goes to 1 of 3x plus 4. No problem here. This denominator doesn't give me an issue. It goes to 7. Numerator, when I evaluate 1, goes to 6. So that one pretty straightforward. But when we come down to these next couple examples, you can see that we run into some problems where if I think I can plug in 3, I can't. But I've got difference of two squares in the denominator, so the limit as x goes to 3 of x plus 3, x minus 3. Look for things that factor, different things you can try to try and clean up, for lack of a better term, your expression. And if I can factor this numerator, which is x minus 3x plus 2, all of a sudden I can get those guys to clear out. So I have the limit as x approaches 3 of, in the numerator, x plus 2, in the denominator, x plus 3. So now I can take the limit of the top, the numerator, x plus 2 over the limit as x approaches 3 of the denominator, which gets me 5/6. So we just had to get what would have been a hole if I were to graph this. We had to kind of clear that out before finding the limit. Similarly, here in B, you can see that we run into a problem. The limit as x goes to 0. I gotta do something with that. I can't factor this x out. You cannot do x 5 minus sine or something like that, right? The sine argument x is not able to be factored. So what can we do? Well, it's a subtraction, and I've got a fraction. So let's just, unless maybe you think of pause and think of something else to try. As x goes to 0 of what I can do is call this 5x over x minus sine of x over x and break up the fraction. Now I get those guys to clear, which is great. And I've got a difference here. So the limit as x goes to 0 of 5 minus the limit as x goes to 0 of sine x over x. Now the constant rule here for the first term, that's just going to be 5. That's no big deal. This guy, I've still got a problem here with sine x over x, taking x to 0. I end up with 0 in the denominator. But if you recall the work we did last week, in 14.1, we defined this particular expression that ended up being equal to 1. And that's a special definition we're going to use, and will come up a lot as we move forward and as you go forward practicing these limits. So that's the only one we have right now, but be ready for those. This last couple problems here is some practice with all of these polynomial and factoring rules. And in this particular case, if I were to plug in 2, I'd run into some problems. So it looks like we're going to probably need to factor. And if you remember how to factor higher degree polynomials, if it's written nicely, correctly, grouping we should be able to use. So looking at the first 2 terms in the numerator, I can factor out x squared and I'm left with x minus 2. I can factor out a 4 and I'm left with x minus 2 from the second 2 terms. And that's not a coincidence. Your goal is to get these binomials that are the same. In the denominator, again, looking at the first 2 terms, there actually I can take out x cubed and I'm left with x minus 2. Now, nothing really to be factored out other than a 1 from x minus 2, but I'll go ahead and do that. And if we rewrite this, this is equal to, let me fix this, there we go. This is equal to the limit of this entire thing. So the limit x goes to 2. If we clean this up, I can group the x squared and the 4. They are being multiplied to the x minus 2 over the x cubed plus 1 and the x minus 2. There we go. So that's going to cancel those out, which is equal to now the limit as x goes to 2 of x squared plus 4 over the limit as x goes to 2 of x cubed plus 1. And if you're thinking that that's the sum of cubes, and which it is, and it has a special factor pattern, the good news is I don't have to worry about that. The reason is I'm just asked to evaluate this limit, and as long as if I can plug a 2 in there and this thing doesn't go to 0, I'm fine. It goes to 9 in the denominator. The numerator, when I evaluate the 2, goes to 8. So the limit of that polynomial is 8/9 as x goes to 2. So we needed to factor to avoid the dividing by 0 problem. Once we took care of that, no extra need to factor any special rules there. The last one for our notes here is the average rate of change, which, remember, simply is the change of y over the change in x, which is equal to the difference of the y's from x to 2, so f of x minus f of 2 over x minus 2. That equals x squared plus 3x minus 10 when I evaluate the f of 2 over x minus 2, which is equal to, if we, let's see, you can factor this, that's x plus 5 and x minus 2. Well, that was nice. X minus 2 there. Those are going to cancel. So that entire change, average rate of change, ended up just equaling x plus 5. That's the rule when you go from 2 to x. Now I want the limit as x approaches 2 of this average rate of change from 2 to x, which I now have defined as x plus 5. So the limit of that equals 7. So calculably, algebraically, not difficult to get to this point. You just had to recall what your average rate of change rule was. And so it's the change in y over the change in x, or f of x minus f of 2, that change. These are both y's in the numerator up here, divided by the change in x minus 2. So that should help you get started and refer back to these for the problems on the homework. And otherwise, I will see you in our Zoom meeting either later in the period or next class.